Yeah, good morning, everybody. It is my pleasure to have with us Maia Vergniory. One is tempted always to, at least me, to start by saying, yeah, we have today a young and promising researcher. She's definitely young, still,
for the young.
but she's no longer a promising researcher. She's already a consolidated researcher. She got her PhD in Basque Country, right? With your supervisor was Pitarque, I guess. From the very beginning, you were working on density functional theory calculations, electronic structure, things like that. She moved to, I have it here, to Lawrence Berkeley National Lab as a postdoc, and then to this Max Planck Institute of Microstructure Physics, again as a postdoc. And then you won the L'Oreal Award, right? In 2017. And you got an Iker Basque fellowship. I think you still have it, right? Or
no.
You will try to explain this now if you want. Because now you are a professor at Max Planck Institute for Chemical Physics of Solids in Dresden, and associate to the Donostia Institute International Physics Center. So you are no longer Iker Basque.
No.
Anyway, so she has been always working on the band structure related things, theory, simulations, computation. But she took it to a whole new level at some point when she decided to join the army of topological people, right? And she did a huge, amazing, and impressive work in this subject. She's co-authoring papers that are now reference for all of us in the field, those interested in topological physics. And I guess today she's going to tell us about a little bit of everything in this regard, right? So please feel free to start.
Okay, thank you, Juanjo, for this flattering introduction, and thank you everybody for coming. So yeah, I'm gonna talk about the role of topology in condensed matter, and I hope that by the end of the talk, I will convince you that it's actually everywhere, and that maybe we need to reformulate the whole field of condensed matter physics introducing the very phase. So why condensed matter? Why I like condensed matter physics? So condensed matter physics has very interesting applications, and it's very, very important. But the reason why I feel fascinated by it can be summarized in this title of Grigor Bolovic's book, The Universe in a Helium Droplet, where he makes this romantic statement that a helium droplet is by itself its own universe. So when we look at materials, when we look at the dynamics of electrons, we can actually see many features from high energy physics that can be actually measured in our materials, and the role of the very phase has been fundamental to actually find them. For instance, we can see the gravitational anomaly, Majorana, Weil, and Dirac fermions, axial Higgs modes, the chiral anomaly, and of course, maybe this will not tell us anything about the origin of the universe because we don't have the relativistic effects, but it gives a solid background to the standard model, and it's beautiful. I don't know. So what are materials? Materials are atoms arranged in a lattice, and we have ions and electrons interacting. So in condensed matter physics, we can make two main approximations. We can consider each electron independent within the single particle picture, or we can consider strong correlations, and then we need to consider the many-body wave function and more long-range phenomena. A very standard example of what I just said can be given with cars. So imagine that we have just one car in the world. It would be very easy to drive. We can go up, down, no other cars will be found on the way, no accidents. Or if there are other cars, they are ghost cars, so there is no crash, there is no traffic jams. Whereas when we consider the many-body interactions, we need to consider other cars, and we can have accidents, and we need insurance, and we have traffic jams. So there is an emergent phenomena that was actually mentioned by Philip Anderson in this paper, More is Different, and there is new emergent physics, and we need new physics rules. So it's in this context of a single particle picture many-body wave function materials where I want to place topology. So why topology? why topology has become a hot topic in the last decades. And the more I know about topology, the more I think that it has become very important. Well, as I said, it's everywhere, but also because it's a coarse property of the system. And coarse means burda. So topology is like a radical approach to the properties that simplifies everything to the limit. And it has very interesting properties. Sometimes they are useful, sometimes they are not, but they are not difficult. I mean, as difficult as also other phenomena to figure out. So for example, if we consider the 5 Platonic polyhedra, if we look at it from the eyes of geometry, we have angles, we have areas, we have volume. For topology, they are all the same, just connected lines. And they all fulfill the same equation, which is that the number of vertices minus edges plus faces is equals to 2. I mean, from the eyes of topology, there is no difference between all of them. And 2 would be this topological invariant. If we go to the classic classification of matter, using the Landau theory and the observables, here again, there are 2 standard examples. For example, we have liquid water versus ice. So when water is in the liquid phase, translation is invariant, rotation is invariant. Every molecule is like a repetition of each other. When we go to the solid state, what happens is that they crystallize, so some symmetries are broken, translation is broken, and we have a different density. The observable would be the density. Another example is non-magnetic versus magnetism. When we have a non-magnetic system, rotation of the spin is preserved. When we let our sample magnetize or we apply a magnetic field, they pick up a particular direction, and the observable is the magnetic moment. And this is how we can classify the different phases of matter, looking at local observables like the density, the magnetic moment, the polarizability. Topology is somehow a hidden order. So we have systems with the same symmetry, same size, same everything. And they display different transport phenomena, because topology is a hidden order, but it's global, not local. This is why it took some time to figure it out. So one case is lead telluride and tin telluride. They have the same crystal structure, more or less the same number of electrons. It happens that lead telluride is trivial, and tin telluride is topological. It has topological features. And in this case, the topological feature of tin telluride, as we find this very robust surface state when we cleave the surface. So it's a hidden order of materials, and it's very interesting, but we need new physics to actually figure it out. And it happens in the single particle picture, but also in the many body wave function. So just I want to give some rough general view of how it's classified so far. And I pick up this 2-dimensional example, because topology in 1-dimensional is not as clear as in 2D. And the spatial topology can be defined by the number of holes. So we can have a plane or a sphere, a donut, and 2 double and triple handle. So if a spatial topology, if we have a spatial topology, it might happen that the number of ground states is different for each of the manifolds. So for instance, for the sphere and the plane, we have 1 ground state, but for the torus, we can have already 4 ground states. So a heuristic definition of topology could be that if we have a spatial topology and we have a different number of ground states, we can claim that we have a hidden or an intrinsic topological order. And one way of defining the number of ground states is given by an integer to the power of the genus. So this is like the rough, broadened classification of topology. It can be given by the topological entanglement entropy that tells us the long range of entanglement in many body systems. And so far, there is 2 classifications. One is when the number of ground states is e to the power of this topological entropy to the power of the genus. When this happens, for different values of gamma, we can have different topological phases. So already for gamma equals 0, we have a completely universe. So we have the integer quantum Hall effect, quantum spin Hall, 3D TIs, topological crystalline insulators, anomalous quantum Hall effect. And for gamma different from 0, we have the fractional quantum Hall effect, the abelian. So this has been measured in gallium arsenide and in graphene. But it can happen that the number of ground states is smaller than this quantity, and there we can have even more interesting features like the non-abelian fractional quantum Hall effect and non-abelian anions. So if many body physics are mind-blowing whenever we look at materials and we have this emergent behavior like superconductivity or spin liquids, with topology it's even more. So I'm gonna focus in gamma equals 0. I'm just going to consider one ground state, and already there is a lot of things to do. But I'm gonna start with band theory insulators, because the way we diagnose topology for band theory insulators or for correlated insulators is completely different. So for band theory insulators, the gap is given just by electron counting. We have our Hamiltonian, we diagonalize it, we get the eigenvalues, we have this number of electrons, we fill the bands, we reach a gap, and that's it. But for the case of correlated insulators, it could be that by electron counting we have a metal, but when we look at experimental data, for example, we have a very large gap. So this large gap can only be given by the many variable function, and it's called a Mott gap. But I'm going to start with this part, and I want to give some historical context. Okay, for those who have no idea about what is a topological insulator, and I know there is at least one, this is a topological insulator. So it's a material that is insulating in the bulk and conducting on the surface. And you can remove the metallic surface and it will not go away. You will get another one and another one and another one. So it's very, very robust. If you look at this picture, it's very easy to understand. Tomato is insulator, I think, and the can is conducting. The thing is that here we have two materials. The topological insulator is just one material with the properties of the tomato can. And depending, there is a crossover between topology, dimensionality, and symmetries. And depending which symmetries are present in the number of dimensions, we're gonna have one type of edge state or another one. All started with the quantum Hall effect in 1980 when von Klitzing measured this very robust quantized current in a 2D semiconductor at very low temperature and under a large magnetic field. And the quantization and robustness of this current could not be understood by the physics that existed by that time. The current could be understood, but the robustness was not. So it was a few years later with the TKKN invariant and the formulation of the very phase that it was understood that this robustness came from the topological order, and what you find is like edge states in some of the edges of the system. A bit later, in 1988, Haldane proposed that one could also see the same effect in a 2D material with an intrinsic magnetic moment. Instead of having an external magnetic field, there could be an intrinsic magnetic moment, and it could reproduce the same topological features. And the two requirements are that time reversal symmetry needs to be broken, and this quantization only exists in 2D dimensions. Then if you have a gap and it's inverted, as I said, topology is like coarse, so you're gonna have the same feature. But for many years, it was believed that it only exists in quantum Hall effect systems till 2005, when Kane and Melle, in their nominal paper, try to put together two Haldane models, one for a spin up, another one for a spin down, because yes, here they just stated a spin polarized current for one direction of the magnetic moment. So they put two together, glued by time reversal symmetry, and what they found is a new topological phase, was called quantum spin Hall. And instead of having one edge state, we have a helical edge states, one for positive, the other one for negative spin, around the whole edge. And in this case, it can only exist in 3 dimensions. So the requirements is fine reversal symmetry needs to be present, and we need to have a spinor recoupling. I mean, it has to be with fermions. And later on, crystalline symmetries start playing a role. They saw that in some materials, topological phases could be protected by inversion symmetry or mirror symmetry, and the edge state would only exist in the facets where the symmetry is preserved. So different dimensions, different symmetries present absent gives different surface states or edge state, which is called the bulk boundary correspondence. So why is this happening? This is happening because of the Berry phase. So the Berry phase is the geometrical phase that, in this case, an electron acquires after performing a closed loop. And this geometrical phase was neglected because if we have an open path, we can always make a gauge transformation and get rid of it. But Michael Berry proved in 1994 that if we have a closed loop, it's gauge invariant. And if it's gauge invariant, it means that it can be measured somehow. And once you learn the concept, then you think it's not such a complicated concept. It's subtle, of course, but it's not like something that needs a crazy mathematical formulation. But it was missed for many, many years. Till I think the first signature of this existence was with the Aharonov-Bohm effect, because the Berry connection and the potential vector are the same, and you can measure some interferences, but it was still 1984 when it was formulated by Berry. So what's the observable? The observable is related to transport and is the whole conductivity, and is quantized because we have a topological invariant in this case that is called the Chern number. So in the Euler polyhedra, we had this one topological invariant that it was 2. In this case, we have also an integer called Chern number, and this Chern number in particular is not bounded, but it gives us the quantization of the conductivity. So how do we calculate the Berry phase in condensed matter physics? We need to go to reciprocal space. We need to go to reciprocal space because we need a closed surface, and the Brillouin zone makes it happen. So real space calculations are complicated because we have many atoms, non-diagonal hoppings, limited by the size. But if we go to the reciprocal space, we can get all the properties of the system from the Brillouin zone, and we have a new quantum number, which is k. So we have our energy levels as a function of k. And here we see that we have lines that are connected and then split and they're connected again. And since topology is the science of connecting lines, we can apply topology to our systems. So for topology, when we are in 1 dimension, we don't have a line. We close it in the Brillouin zone, we have a circle, and we map it to a circle. And when we are in 2 dimensions, a 2-dimensional Brillouin zone for topology is a torus that we can map it to a sphere. So now we have a closed manifold, and we can calculate the Berry phase. So I said applications are not the main thing, but they are still important. And there are many potential applications for topological materials, environmentally friendly technology. Transport properties are very interesting in these materials. We have quantum anomalous hole, spin hole, Nernst effect, nonlinear optical transport, magnetotransport, topological surface states with very low dissipation. Catalysis, there are some proposals for catalysis using the surface state of topological materials are catalytic agents. Spintronics, they are structurally chiral topological materials that have very interesting spin textures. And as I said, quantum computers in some correlated regime, we can have the non-abelian anions, and these are very interesting for applications. Okay, so the first classification of topological phases was given by the tenfold classification of Atlan and Zimbauer already some time ago. And it was based on this intrinsic anti-unitary symmetries. So time reversal symmetry, particle Hall, and chiral symmetry. It's unitary chiral symmetry. So these are the name of the classes. These are the symmetries, the square of the symmetries. So whenever time reversal symmetry is applied to bosons, it squares as +1. When it's applied to fermions, it squares as -1. And so depending whether these symmetries are present or absent as a function of the dimensions, we can have here the classification of the topological phases. So class A, for example, time reversal symmetry is not present, neither particle Hall, neither chiral symmetry. It's the quantum Hall effect. It doesn't exist at 1 dimension, but in 2 dimensions we have the third number, and only in even dimensions. And here in class A2, time reversal symmetry squares to -1, and we have the 2D and 3D topological insulators. So actually, this table is very convenient because it also includes superconducting topological insulators and these things, but it's only based on intrinsic symmetries. However, given some historical context, it actually helped to discover several topological materials, starting with mercury telluride in 2006, then bismuth selenium 2009, 2010, and related family in 3D. This was important, at least for us, because it was Liang Fu and Taylor Hughes and some people that introduced for the first time the crystalline symmetries as potential symmetry to classify topological phases outside the original table. But it was at the beginning, there was no way to actually how to include this classification in the table. And then with symmetries, also Dirac and Weil semimetals appear, high order nodal points, nodal lines, and high order TIs. However, till 2018, 40 years after the quantum Hall effect discovery, only of the order of 300 topological materials were discovered, which made everyone believe that there was some exotic thing of nature that was only given to some selected materials. And it was not the case. The missing part was that the relation between topology of real space and reciprocal space was still not clear. And this is what topological quantum chemistry is about. So it combines first principle calculation, computational physics, and ground theory in order to connect real space with reciprocal space and give a full topological classification. Performing the full topological classification is when accidentally we discover that topology is actually a very present property of band structures. So we have in non-magnetic groups 230 space groups with the properties of lattices, unit lattice translation, point group operation, non-symmetric symmetries, orbitals, and some atoms in some lattice positions. So one of the most important definitions that was given by Vanderbilt and Alexei Soluyanov is what is a trivial insulator. And a trivial insulator can be described by the Vannier functions. Vannier functions are the Fourier transform of the Bloch states of some bands to real space, and they have a Vannier charge center, which is in the end is given by the vector operator, and we have a trivial insulator when these Vannier centers of the particular orbitals that form these bands are exponentially localized in the atomic sites. So if this happens, our gap is trivial, our bands are trivial. So the definition of topology can be, if it's not trivial, it has to be topological, and then we will discuss what is the topological phase. But at least the charge would not be localized in the atomic site. Yeah, I mentioned the Vannier centers, and the Vannier centers are these are given by the position operator. When we are in 2D, we need to actually calculate the hybrid Vannier centers which is the position operator in one direction as a function of the kx in the other direction. And what we see is this winding. And this winding is actually proportional to the value of the very phase. So whenever we have a non-zero very phase, we have a winding of the Vannier centers. Okay, so this was formulated by, this is the work of David Vanderbilt in the last years, and it was very important to actually be able to diagnose topology. But it was not very practical because computational cost was at the beginning, especially at the beginning, was expensive. Vannierizing a Hamiltonian would take time, I mean, so on and so forth. So it was not easy to actually perform a high throughput calculation. This became a reality when we found that there was a way to connect real space with reciprocal space in a very efficient, fast way, and it was given by the elementary band representations. So elementary band representations were introduced by Michel and Zach. It's the work of Zach, who wanted to understand very deeply the band structures, and he wanted to find a center of mass that would connect the band structure with the real space. And this is the elementary band representation. It's a set of bands that are given by three ingredients. So are the PC orbitals, the Bikov position, and the lattice. And these three ingredients give us at the high symmetry points specific and unique little groups for all the bands. Instead of having PC orbitals, we have Px and Py orbitals, we get other irreps. Okay, so the connection is an elementary band is irrep, lattice, Bikov position, and these ingredients give us uniquely the little groups at the high symmetry points. So the connection with topology comes from the fact that an elementary band representation that gives us this information is nothing but the atomic limit described by Solujanov and Vanderbilt. So if we have an elementary band representation, we have actually the information to create a Vannier basis that describe this atomic limit. And again, what was the claim from Michel and Zach is that elementary band representations, which are these set of bands, are always connected. And they are always connected only if they describe an atomic limit. So when these three ingredients from real space, they are not connected in reciprocal space, it's not an atomic limit anymore. So if it's not an atomic limit, it has to be topological. So basically, this is how it works. We have our lattice, we have our wave function and some Bikov positions. We get connected ones in reciprocal space. This means that the charge is exponentially localized. There is no very phase there. On the contrary, if the opposite happens, we don't have a Vannier basis exponentially localized that respects all the symmetry. We will have disconnected bands instead of connected, so the charge is gonna do something else but being exponentially localized. So now the way to look at topology is by looking at the irreps at the high symmetry points. And this can be done very fast with the FT codes. We get all this information and we can tell whether a material is topological or not. I mean, it has finite very phase or not. So being so fast, we said, okay, why don't we scan a full database instead? Right now, with 5 minutes run, we can get the topology of one material. Let's scan it completely and see how many topological materials are in nature, with no idea about what was going to be the result. But also, we decided that since we need to calculate the full spectrum of the band structure, why don't we look at the topology of every gap? I mean, there is no reason why to just look at the Fermi level. I mean, there is a reason because experimentalists are interested in the transport regime, but for us, we want to understand a bit more what's the role of topology in materials. We can actually scan the full band spectrum. And it happens that sometimes could be that at the Fermi level, you have a trivial gap, but the one right below is topological, or the one right above. Sometimes there are gaps that are all topological, like in the case of bismuth. And it also happens that materials like this one, who were believed to have a topological surface state at the Fermi level, but then bulk resonances, it happens that this bulk resonances can also be described by topological indices, so they were also topological. So, okay, so after that, the result was like topology at the Fermi level. We have protected crossings, which can lead to topological semimetal. And the green part are topological insulators. And the orange part is related to the trivial phases. So there are not as many trivial materials as we thought. And if we look at any filling, it happens that 80% of materials have at least one topological band. So again, Berry phase is very present in band theory, and it might affect many of the transport properties that we know nowadays. We could also do it for magnetic materials. So magnetic materials present an obstruction to have a Vanier basis if we use regular orbitals, but if we use magnetic orbitals with time reversal symmetry broken, then we can actually get a Vanier basis, define the atomic limit, calculate the magnetic EVRs. And the rest, it worked in the same way. So it took a lot of time to implement all this because the magnetic co-representations were not in the literature. Magnetic codes did not preserve magnetic symmetries, and the topological classification was needed. Another issue is that there are not magnetic databases as they are in non-magnetic materials, and we wanted, DFT has problems getting the ground state of a magnetic material, so we wanted actually materials whose magnetic structure was measured by neutron scattering, and there are not that many of them, but still, so we got of the order of 400 materials, and 130 had no trivial topology for certain values of U, because we made for each material a phase diagram as a different value of U and J to reproduce the experimental features. So it's also present in magnetic materials. There was no reason not to be there. And also new topological phases arise after this work. The higher the TIs, where the bulk boundary correspondence goes from the bulk from 3D to 1D with these hinge states in bismuth, the fragile phases, obstructed atomic insulators. These materials actually originally lied in the trivial ones, but then they are not really trivial. But anyway, that's also another story. And then action insulators, depending on the symmetries, a high order magnetic topological insulator has different bulk boundary correspondence at the hinges. And everything has been updated online. If anyone, for the magnetic, non-magnetic, and the obstructed atomic limit, if anyone wants to look for a material, there is this database that we try to update where the topology is described. All the codes are available. The classification is in the Bilbao crystallographic server, and Python package to actually calculate the reps from state-of-the-art ab initio code has been given. Are in this repository. Okay, so what about phonons? Can we apply the same formalism to phonons? And in order to answer this question, Martin considered the Backel honeycomb lattice in 2D. So now we don't have a wave function, we have a vector. We need a vector representation, but in the end, it works in the same way because we just need to adapt the formalism to this vectorial formulation. So he developed a tight binding model. He looked at the compatibility relations between the bands, and from this analysis, this is pure analytical. From this analysis, he found that we can have 11 different gap phases in the Backel honeycomb lattice, and 5 of them are topological. Using topological quantum chemistry, this IREP analysis. But then we wanted to make sure that this was the case, that we were not like claiming that topological quantum chemistry could work in phonons without actually not taking it. So we calculate the winding of Vanier centers for these tight binding models, and actually yeah, I mean, we could see that our topological phases predicted by elementary band representations agree with the winding of the very phase. And then we decided to use it for several materials like phosphorus, antimony, arsenide, silicon, and germanium. But it happens that all of them were trivial. So reaching these topological phases in phonons required long-range force constant, and this is not something straightforward to have in a material. But still, after this, okay, we saw that we could apply topological quantum chemistry, and we did exactly the same thing as with electrons, scan a database. In this case, phonons were calculated in the Kyoto and in the materials project, which is very nice because calculating phonons is tricky and it's not like electrons. So we apply the machinery in the same way, basically, with the same ground. And we found that we actually have topological phonons less than electrons, which makes sense in a way that first they are bosons, time reversal symmetry squares 2 + 1. So we have less topological phases, and then they are bounded by the force constant. So if we need some sort of long range force constant to actually move the maximum of the amplitude away, maybe it's more tricky than with electrons, but still they are materials with topological phonons. Since we calculated all the phononic bands, we also put in this paper some materials that have interesting instabilities in a way that they can be stabilized with temperature, so probably they are describing charge sensitive waves. And again, everything has been uploaded in the database. Now, still dealing with, let's say, mechanical systems, I want to mention a little bit topological photonic crystals. So we apply the same formalism to topological photonic crystals. This was done by Maria Blanco de Paz. Her PhD work, and she developed all the scripts and codes to actually be able to calculate the IREPs and apply to these different geometries. And well, we found that topological, this formalism also works for photonic crystals, and again, it's very fast because we did it for this geometry with dielectric rods with different sizes, and we could make this phase diagram as a function of the diameter of the rods. And I think she did it in 2 days, whereas if we needed to calculate the very phase and things like that, it would have taken months. Another interesting application, not of topology, but of elementary band representation, is that we can we can implement 3D tight binding models for photonic crystals. So the problem of photonic crystals is at gamma, because we have 2 transversal modes that create a singularity, and it happens that we cannot assign an IREP to the gamma point as we did with the electrons or phonons. So if we want to have a tight binding model, because for instance we want to calculate surfaces or hinges, and this is what we wanted, we have the problem of gamma, that we have these transversal modes that cannot define an IREP, and then it stops us from getting a tight binding model. So the idea here, I'm going to say it very fast, but see if I can do it well. So the idea here is that, okay, we don't have the IREPs at gamma, but we have the IREPs in the rest of the high symmetry points. So usually what we do is from the orbitals we calculate the IREPs, and from the IREPs the tight binding, and here we are going to do it all the way around. We are going to consider all these IREPs, get the elementary band representation, and from this get the pseudo-orbitals to define the tight binding model. And this is done by adding some auxiliary modes to the transversal mode at gamma, by being able of actually define an elementary band representation from the information we have here. So after this was done by Antonio, who will be here next week, so in case anyone wants to talk to him, And he actually found a way to actually optimize these auxiliary modes and be able to define a tight binding model that can reproduce topology. And we could use it to actually define a 3D axionic insulator. So, so a 3D magnetic high order TI has an axionic response that is very interesting because this has this topological magnetoelectric response that it's quantized. We also have the action photon coupling that there are some proposals that they can actually measure the dark photons, but it's also very interesting because we can have tunable chiral 1D hinge channel. So the work we did here is actually, we start with a crystal. With photonic crystals, it's nice to work because we can manipulate them in the way we want. We start with a crystal that has a crossing at a high symmetry point. We enlarge the unit cell, so we get the bands folding, and then we break some symmetries to induce a modulation, which would be like a charge density wave. So inducing this modulation, we open a gap, and this gap is actually described by Chern numbers. Yeah, we apply a magnetic field to split the vials. So if you open the gap of vials, then your gap is going to be topological. And as a first approach, what we got is very interesting surface state defined by the different values of Chern number. By turning the magnetic field, we can get one hinge state, one surface state, or two, or even up to 4. And one would think that this is okay, this is just playing theoretically, then experimental is a challenge, and it is a challenge, but it has been done in China, in the group of Bailey-Sang. They actually reproduced this in this experiment in another system, but with the same idea. And then we wanted to have an axionic response, which is a hinge state, and for that we needed to actually have a different phase between the different modulations, and this is what we did. So in order to interface these two different phases, what we did is put one, let's say, wire inside a second wire, and like this, in the interface of these two, we can get these hinge states. And on top of the fundamental reasons, it was very interesting because we can manipulate the hinge as a function of the magnetic field, but also because it's embedded in bulk, it's protected from electromagnetic radiation. So this was up to the single particle picture. And now, so what's next? So next is like, okay, let's try to see what happens if we add correlations to our systems, and how can we see topology. So the first idea was to look for topology in heavy fermions for several reasons. There are none, almost a topological heavy fermion system. And then this is what we have in a heavy fermion is hybridization from dispersive bands with localized bands. But these dispersive bands, in our case, were d electrons, and these are f electrons. So we're going to have many bands. So if hybridization happens with many bands, means that we're going to have many gaps. So this comes to the fact that we could have many topological gaps, which is called cumulative topology. And this would be very interesting because this means that it doesn't really matter where you are around the Fermi level, because you're going to have these topological properties at different above and below the Fermi level. So actually, DFT has its limitations, but the interesting part of DFT is that it sometimes works when it should not work. And this is the case of samarium hexaboride. And we couldn't understand why DMFT calculations and DFT calculations, of course, the size of the gap was different. Bands were renormalized, but the symmetry of the bands was the same. Like experimental IREPs agree with the IREPs we calculated with DFT. And the reason is the following. So it's the filling. So samarium hexaboride is a mixed valence because the valence electron oscillate between 5 and 6. And because it has this very particular filling, it happens that the DFT bands and the DMFT bands have the same symmetry. So in DFT, the lowest, I mean, the bands at the Fermi level have these J equals to L plus minus 1/2, which is DFT, and it's like that. But if we go to the spectral property from the many-body wave function, if we go to the lowest energy level, it happens that, and applying the Hahn rules, it happens that the symmetry of the lowest energy bands have the same symmetry as the DFT bands. And this is why it works. And since topology is this brutal, then we will have the same symmetry of the bands. It doesn't matter if the gap is larger or smaller. The topology doesn't care about that. It's going to work in the same way. And this is very convenient because then we can apply the topological quantum chemistry machinery, which is very fast. Again, very fast, very straightforward, very easy. So we calculate the bands at the high symmetry points, we diagnose the rep, and if we look at the gaps, we see that we can get the full topological classification as a function of the indices for the band, for the gaps below at the Fermi and above the Fermi level, and there is cumulative topology. All of them are topological. And these indices tell us about many different surface states. So for instance, this is in the Topological Quantum Chemistry website, but this index corresponds to the strong index, C4 = 1, so it's a strong TI. And this one here, it corresponds to C4 PM. That tells us that actually we get 5 because the Chern number is equal to 1. So we have a mirror Chern insulator. Then Mikkel developed a tight binding model. We calculate the winding of the Vanier centers. It agrees with the index classification. And as a consequence, we'll have the surface state at gamma and X that have been actually seen by ARPES. But there is a point where we really need to go beyond DFT, because when we are dealing with Mott physics, maybe we can get the gap, but then the reps does not work anymore. And also because we realized recently that topology is way more complicated than just looking at the reps. So the motivation came from copper bismuth oxide when we were implementing the topological database, because I thought it was very interesting metal that worked with crossings at the Fermi level. And it happens that when you look at the experimental gap, copper bismuth oxide has a very large gap. And with DMFT, they also got a very large gap. So it's actually not a protected metal. It's a Mott insulator. So now we're gonna start with this part that corresponds to correlated insulators. So we wanted to look at the role of symmetries in actually these systems that we're DFT are metals, by electron counting are metals, but when we add correlations, they become insulators. The question is like, the gap of this system is different from the gap that are already insulator in the single particle picture. And in order to use topological quantum chemistry, we need a lattice and crystalline symmetries. And with those ingredients, we can already play around. So the system was a simple one, the one they have our chain with 2 mirrors in X and Y, and 3 hole pins. T and 1 are in the diamond, and T3 is connecting the diamonds. And we add a Havard U that doesn't break any symmetries because we don't want to break any symmetry. So this is the phase diagram for the different hole pins. We have an atomic insulator, an obstructed atomic limit, which is also an insulator. And here in this part, we find a metal. And this is the phase diagram as a function of the different hole pins. And the interesting part, of course, is the metallic phase, because we want to see what happens with the metallic phase. So since T1 is the dominant hole pin, we have, and in the half-filling regime, we have a metal that is given by these bands. We have a flat band crossed by a dispersive band, and it reminds to the paper of Yao and Kibelson of 2006. And I want to mention it briefly because it's also related to what we discussed in the colloidal systems. So we have two Hopins and a square lattice. And what they claim in this paper is that the many variable function without interaction needs to transform trivially under the point group of the lattice. So if we apply, I think it's C4B to the many variable function, we get the many variable function back. When they start playing with the Hopins and with a value of u different from 0, what they saw is that they could see that a wave function was actually transforming trivially, which means in this way as a function of the symmetry operations, but there was another wave function that was transforming non-trivially. So here they would get a minus. So this phase and this phase are not adiabatically connected, and the localization of the charge is different. In the S case, it's localized in the center because T2 is the dominant Hopin, and in the D case, it's on the edges because T1 is the dominant Hopin. So depending on the dominant Hopin, we get different charge, and when we get different charge, we can have interesting features, charge localization. So we did the same thing for our 1D chain, which is a simpler version of the square lattice. So for the atomic limit, with these Hopins, it transforms trivially under the irreps of the point group. And when we go to the metallic phase, it happens that it transforms non-trivially because we get another irrep that represents the symmetry operations. So we use exact methods to actually see if we could get a gap here, and we got a gap here. So we have a metallic phase with mean field approximation that becomes insulating with correlations, and it transforms in a different way as the trivial part. Introduced by this paper of Frank Pullman, we could actually get some sort of invariant that shows that this Mott insulating phase is non-trivially connected to the other phases. In this case, it's -1, and the other one is +1 as a function of this mirror symmetry, which is the symmetry actually protecting the phase. And by doing some twisting maths, we could also differentiate these two phases, but this it doesn't matter. So now is okay, with exact methods, we can get these differentiate these two phases, but we want to actually use it for materials, and for materials we cannot use exact methods. So one way to go is by using Green's functions. So the single particle Green function, let's see if we can get this information from the block spectral function. So we use cluster perturbation theory that actually calculates the Green's function of the cluster and then embed it in a perturbation in a bath. With this Green's function, we use the formalism of topological Hamiltonian that actually is a non-Hermitian quantity given by the inverse of the Green's function for zero frequency. And Dominic Leschnyz, a student of Rosé, he developed the conditions in order to be able to use it. So, okay, for the other phases, this formalism works very well, but it happens that for the Hubbard bands that we get for the Mott phase, with the Green's function, we get the gap, which is good, but then the self-energy diverges, and if the self-energy diverges, we cannot get the topological Hamiltonian. So single particle Green's function is good to get the block spectral function, but not the topology. A step forward was made by T2's group in Zurich. They calculated the two-particle Green's function, and with the two-particle Green's function and considering instead of one diamond, several diamonds, then they could actually predict the existence of topological phases in these gaps. But again, it's very difficult to use this for materials. So then we all went to KITP this April, and we talked with Chindan and Chimiao and Silke, and there were many ongoing discussions. And one possibility that arises is that why don't we calculate just the very phase? We go back to very phase. But of course, to calculate the very phase, we need an Hermitian-Green's function. So by looking at papers of Gurari and Bolovic, they show that we can actually map the Green's function, the non-Hermitian Green's function, to an Hermitian Green's function by defining this G plus minus, which is the retarded plus minus the advanced Green's function. So we get rid of the complex part, and by having this Green's function as a function of omega, then we can calculate the very phase and the Chern number as a function of omega. So we can block diagonalize our Green's function, get the eigenvalues and eigenvectors. So we calculated the very phase as a function of omega and the Chern number as a function of omega. We use this model where we have tetragonal lattice with that actually when we break time reversal symmetry, we get two vials, and when we add correlations, the vials open. And we want to ask whether the gap from these vials is actually topological. And the interesting part comes from, doesn't come from the poles. The poles give us the block spectral function and the quasi-particle information. It actually comes from the zeros of the Green's function, because the zeros of the Green's function in this model have the same dispersion as the original vials. So these are our Hubbard bands, but these are our original vials, now described by the zeros of the Green's function instead of the poles. So if we calculate the very phase for different values of omega, it happens that we get the same Chern number, but at some point we get the opposite Chern number. And when we get the opposite Chern number, we get the opposite Chern number when the Green's function reaches a zero. When for the values where there are no vials, we get Chern number equal to zero. So the Chern number actually comes from the vials. So in summary, what we found, and it's still difficult to understand, is that we can calculate the very phase from this Hermitian Green's function, get different Chern numbers, but the boundary of the change of sign of the Chern number is given by the zeros of the Green's function. So actually, this means that the Green's function zeros is playing a very important role, and we should look at it. So, well, I think we have understood band topology very deeply, and so that it's very important to include the very phase always. We have tried to diagnose topology in Mott phases, and we reached the point where it has to be diagnosed with the zeros of the Green's function. They play a role. They are the boundaries of the frequency-dependent very phase, and we want to actually figure out how to deal with this, because if this happens in the single particle Green's function, we can actually use it for materials. And well, I hope I convinced you that topology is everywhere and that we need to consider the very phase all the time. And I want to thank my students, collaborators, finding agencies. Thank you.
Thank you, Maia, for this enlightening presentation, covering all possibilities. So, time for questions.
Thank you very much for the nice talk. I have a question related to phonons. Okay, so when it comes to electrons, we know essentially that to find a non-trivial topology means maybe the quantization of a transport property and many other things. But what does it mean actually in the case of phonons? I mean, if you find non-trivial topologies, what does it mean?
Well, first, this is an open question, so I can't tell you what I know. It works like if the amplitude, the maximum amplitude of the mode was not in the atomic site, it's outside the atomic site. So it's a mode that has its, say, own lattice. So this, of course, might have important consequences. This is the intuitive explanation. We calculated the edge states. You can have phononic edge states, but I don't know if that can be measured. I doubt it. So as electrons, they have edge states or hinge states when there is a phonon topology, at least from theory.
Thanks, Maya, for the talk. I have a follow-up question about the phonons. So I think you had in your table that you have strong topological phases. So I imagine this means C2. So how does this look for bosonic?
It's a C2 phase protected by crystalline symmetries, not by time reversal symmetry. But it can only happen in 3D.
Thanks.
Thank you, Maya. Coming to the correlated phases, okay, the poles are but they give you the effective Hamiltonian, but the zeros of the Green function, why do they indicate what is the boundary of the phases? So
it's in principle, as we saw, the boundary of the phases, and you have the dispersion of the originally protected chrosins. They are related to non-spectral, they are related to states that have no spectral weight. So it has to be some spin states. But so far, it's just the boundary of the very phase when it changes the sign.
Yeah, thank you. Thank you very much for the nice talk. I have a question regarding the semiconductors. Very often in a semiconductor, you have a state inside the gap. And this state sometimes extends quite a large amount of space. Can you say something about the band structure around those localized states inside the gap?
Are you talking about dangling bonds or Shockley states, or?
Well, I mean, just an impurity, which like phosphorus in silicon, right? In samarium bosix, there are impurities, of course, and these create states inside the gap. Can we say something about the electronic properties of these states?
But in terms of topology, or how?
In terms of topology, if that's possible at all.
The fact that you have topological states inside the gap doesn't mean that you cannot have any other state inside the gap. It's just these particular surface states can be predicted from the bulk. With bismuth selenide and these guys, it happened that they were van der Waals materials, so surface was very clean because you can cleave it. But if it's not a van der Waals materials, you're probably going to have dangling bonds, and these are trivial surface states, and they coexist.
Okay, thank you.
This was the question.
Well, yeah, I mean, you always have some impurity. And
well, if it's a van der Waals materials and it's clean, in principle,
okay.
You can have vacancies. Well, yeah, you can always have impurities. That's the problem of TIs, right? That the gap is very small and it's very difficult to experimentally have a clean gap. But even if there are impurities, another surface state, the topological states should be there too. And for superconductivity, they are important because sometimes they define the pairing, even though there are other trivial states.
Do we have any more questions from the master students? They should understand everything, right? At this point. Yeah.
So what is your view about interactions and topological photonics? Do you think that's interesting at all? So trying to add nonlinearities into topological photonics, and if there may be anything or not at all?
Given what I saw with electrons in the most simplest formulation of correlations, I would think yes. Anything you can, I think it could be interesting to look at nonlinear topological photonics.
I have maybe a question. So in the end, all the properties that can be measured come from the surface states or the edge states, right? The quantization and everything. So what about the bulk? Do they have anything special in terms of bulk properties? Bulk, something that can be measured with, I don't know.
In metallic phases, in vials, yes. In insulating phases.
Is there anything particular that can be?
Transport happen at the edges. So far, we can, I mean, the smoking gun for topological properties is the surface state that we can get with Harper's, and this anomalous hole conductivity, the spin hole conductivity. But of course, this comes from the well, no, the anomalous hole can come from the bulk when you have non-zero very phase.
That's the only case?
Eh?
That is the only example?
That or the nest effect too, but these are there is the nonlinear quantum hole too that could somehow work in 3D, but it's not, I mean, it's complicated because in transport you have everything mixed, so it's very difficult to disentangle. With the, well, you have the circular photogalvanic effects for vials, and that in principle should be quantized.
Any other question? If not, we can, yeah, thank you again for the presentation. Thank you, Maia.